a little bit. Does anybody remember this at all?
Yes.
Right hand rule? Yes, you do remember right hand rule? Yeah. Fingers in the direction, excuse me, yes, you're right. Thumb in the direction of the current. Fingers give you the direction of the magnetic field around that wire. That works for a straight wire. It turns out it works for like little segments of wires that might not be straight as well, as we'll see today. We have this one equation so far that tells us the value or the magnitude of the magnetic field a certain distance away from a wire that has current passing through it, okay? We're going to extend this quite a bit today, but before we do that, let's see, we worked several of these problems. I wanted to do this one as a bit of a practice. It ties together this new concept with our right-hand rule from the last chapter as well. It's a two-step problem. Take a minute, talk to each other, use your right hand, and try to figure it out.
Wire is right
Can we take a vote?
Yeah.
Number 1, 2, 3, 4, 5. Like 5 people voted, I think. What about the rest of you? How about this? Let's start with the magnetic field. We need to figure out what kind of magnetic field this thing is moving through. Otherwise, we don't know what kind of force it's going to be, right? So point our thumb in the direction of this current, and then you can imagine that the magnetic field is going to wrap around the wire like this, okay? So over here on the left side of the wire, the magnetic field is pointing towards you, okay? It comes out of the screen here. In front of the wire, it's pointing to the right, and then over here, it's going into the screen, and so forth, okay? So at the location of this particular charge, what did we just say? We said the magnetic field points out of the screen, and that symbol denotes out towards you, okay? So let's see, we could also write in here on this side of the wire, it's pointing into the screen, okay? Good so far? All right. Now the different right-hand rule for the direction of the force, remember it's Q times V cross B. So we start with our fingers in the direction of the velocity of the charge, and then orient our hands so that our fingers will turn toward the direction of the magnetic field. So I have to go this way, and then my fingers turn in the direction of the magnetic field. Notice which direction my thumb is pointing. To the right. Toward the wire, that's the positive X direction. So with the current going this way and with the charge going directly next to it, it's going to feel a force that makes it turn toward the wire, all right? So our answer here is positive X. Do we need to do that again?
The second part.
The second part. So let's see, for this part we're using FB equals QV cross B. So this is fingers. This is turn fingers. And then this one is thumb. All right? So the velocity is pointing straight up, fingers this way. The magnetic field is pointing toward you, so my thumb points to the right. Okay? You can do this. Right, right, left, right, maybe. Okay? Let's think about this in a little more detail. What if I had two wires that are next to each other, right? Things are getting a little complicated because you can imagine, like, if there's just like no wire down here at the start, this wire with a current passing through it is creating a magnetic field everywhere around it. And you can see they've drawn in some of the magnetic field. Make sure that agrees with your right hand rule. Thumb is this way, which means above the wire, the magnetic field will be pointing at you, and underneath the wire, it should be pointing away from you. Okay, so you can see that that agrees with our right hand rule. Well, that means if I have another wire nearby and there's charge flowing through the wire, then this wire is sitting in that wire's magnetic field. Uh-oh, okay? So you can imagine that this wire is going to feel a force from that wire, okay? Charges are moving through a magnetic field. But I could think about that the other way around as well, right? This wire, since it has current flowing through it, is producing a magnetic field too, right? What's its magnetic field look like? Same sort of thing. Above it, it should be pointing towards you, and below it, it should be pointing away from you. So let's draw in, let's see, some more of these. So this is the magnetic field, let's call it B2, and this one at the top is B1. So this one is creating a magnetic field around it we call B1, and this one is creating a magnetic field around it called B2. Just keep in mind, it's not just right around it, it's everywhere around it. It just gets weaker the farther you get away. So each one of these wires is sitting inside the magnetic field that's being created by the other wire, which means they are going to exert a force on each other, okay? It is a Newton's third law situation. It's an equal and opposite force. If one exerts a force on the one, the other one exerts a force in the opposite direction on it. And we've got an equation for this that I'm just going to give you because of time, and then we're going to talk about the direction of these. So the force between these charges of either one of them actually is equal to mu naught over 2 pi d. This is the distance between the wires, times the current in one wire times the current in the other wire times the length of the wires. And I'm assuming that they're the same length in this particular case because all of them are drawn that way. Why not? Okay? So just like we saw before, if you have a wire that current is going to pass through and you happen to be putting that in the region of a magnetic field, you have to consider the mechanical problem that a force could be exerted on that wire and it could get pulled or broken or damaged in some way. If I have two wires, both of which are carrying current and they're going to be relatively near each other, their magnetic fields interact and they exert forces on each other. So it's another thing to consider mechanically because it could cause problems in a circuit. Now let's see if we agree with what's happening over here. Notice at the top, we're going to see what the forces are if the currents are going in the same direction. They've decided that the two wires are going to be drawn toward each other. Does that make sense with our right hand rule? We can think through it. Your question first.
After you explain this.
You sure?
Yeah.
Okay. All right. So let's start with the top one, that's the same as this one over here. So let's go ahead and use that. Remember when we're dealing with the force on a wire that's carrying current, we start with our fingers in the direction of the current and then let our fingers turn toward the direction of the magnetic field. Thumb tells the direction of the wire. So let's see, what are we going to do with this? So the current is going this direction, but it's sitting in a magnetic field that's into the screen. Okay, so that way for the current, fingers curl this way, the force on this bottom wire is up. Now if you're saying, why did you use that magnetic field? Because this is the magnetic field that it's creating. It's like, can it be affected by its own magnetic field? That doesn't really make a whole lot of sense. It's being affected because it sits in the magnetic field that's being created by the other wire, okay? So here we have current this way, magnetic field into the screen. Gives me a force up. What about at the top? That time I have a current that's this direction, and it's sitting above this bottom wire, which means it's dealing with a magnetic field that points towards you, which gives me a force down. So over in this case, the two wires are experiencing equal and opposite direction forces toward each other. All right? Yeah? More right-hand rule practice, right? What about this one? Notice they've kind of specified a little better which magnetic field we're talking about. So for the bottom wire, now we're going to let the current go this direction. It's in this magnetic field that's into the screen that's being produced by that wire. So we've got current this way, magnetic field away from you, the force is down. Same sort of thing up here. We end up with forces in opposite directions, but equal magnitudes. The wires push themselves apart, okay? Your questions get answered a little bit? Yeah, okay. If you want to ask, let me know. Yes?
What is L again?
L is the length of the wire.
What if they're different wires?
What if what?
What if they're different lengths?
If they are different lengths, then we would need to specify which force we're talking about. For instance, a force on the second wire, we would use the length of the second wire, and vice versa. Anyone else? Okay, so I just answered that question, so we don't need to do that. Skip over that. We're actually not going to do this. Isn't this fun? Don't you love it? Which brings us to something you're going to love, because it's going to be a bit of a throwback to something else you loved. You might start to be guessing. Like right now, you're racking your brain thinking, like, what did I hate the most this semester? I bet that's what he's calling back to. What was it? Whoa, impressive. You hated Gauss's law. Well, Ampere's law is kind of similar, but easier, okay? It works kind of the same way. We're not going to go into it in nearly as much depth, and it turns out the integrals and everything about it is just kind of simpler to deal with because we're going to be working with lines instead of areas, okay? So it's like we take the dimensions down a little bit. It gets a little bit simpler, okay? Ampere's law is a way to find the magnetic field from currents in symmetrical situations. So we can find B from currents in symmetrical situations. And Ampere's law looks like this, and it's going to look a little bit familiar. On this side, we have a closed integral of B dot dl. This is what's known as a closed path integral. dl is just a little bit of a path we're going to integrate around. On the right-hand side, we have mu naught, which is our permeability of free space, times the current enclosed. And this is the current enclosed by the path. There's the equation. We're going to talk about it a good bit. We're going to do two examples, and then it's going to end up in another place as well where we kind of get to practice it, but by that point we'll be talking about something else. Closed path integral B dot dl is equal to mu naught times I enclosed. So you can see in the figure here at the middle, we have a situation very much like what we just learned about in the first slide of this chapter. A straight wire with current passing through it creates a magnetic field. I'm going to show you that we can use Ampere's law to get that equation that we had on the first slide, the one that I put in a box just a few minutes ago, okay? So I gave you the equation, now I'm going to show you where it comes from, which is Ampere's law. So you will notice that they have decided to draw a little path that goes around the current, okay, around the wire that's containing the current. So that path just forms a circle of radius r that sort of wraps around the thing that's creating the magnetic field. We know that at a constant distance away from the wire, everywhere on that path should have the exact same value for the magnetic field. We know that from the equation from before, plus it just sort of makes sense. If as long as you're the same distance from the thing making the magnetic field, you should have the same value for the magnetic field. So let me show you how this works using Ampere's law to calculate this particular situation. So let's evaluate it for that. Everywhere along the path, we can say that the magnetic field is constant, so I'm going to take it out of the integral. So I have just integral of dl. And on the right side, the current enclosed by the path, literally you look at how much current is inside that loop, inside that circle. And looking back at the diagram, it looks like the only current that's anywhere inside there is the current I. So the current enclosed is I. So we just write I. That's not too bad so far. Okay? So what is this integral dl? Here's the way to think about it. If we go back around here, each one of these little arrows might represent dl. dl just means a little bit of the path. Okay? So each one of these is dl, each one of these is dl. If I add up all of those and go all the way around the circle, all I've done is found the circumference of a circle. So before we were doing like surface areas and stuff. This time it's literally just how long is the path. Here, if my path is a circle, the distance around the circle is the circumference, which means that this integral dl is just 2 times pi times r, the circumference of a circle. So this is the length of path. So I have b times 2 pi r equals mu naught times I. And we can calculate b from that, and we get mu naught over 2 pi times I over r, which is the equation we had before. Okay? They're not really going to get much harder than that when it comes to Ampere's law. The key things are, what is the path integral? You have to figure out, am I dealing with a circle? Am I dealing with a square? Am I dealing with a straight line? How long is the path? Figure out what that length is. And on the right side, just how much current lives inside that path. Is there one wire that has current I? Is there 2 wires that have current I? Is there 6 wires that are inside that path? Is there one wire that has current 6I? Like whatever lives inside that path is what you put on the right-hand side.
So let's see. We were talking about Ampere's law, and over the next several slides, even though I'm going to introduce a couple of new things, we're going to repeatedly use Ampere's law to sort of derive the new equations for some new situations. So that's going to give us a little bit of extra practice showing the versatility of Ampere's law. And then we're going to look at the equation that will sort of let you calculate the magnetic field for any situation. If none of the other rules work, you can use this one equation. And then we're going to end our discussion of magnetism by dealing with the materials themselves, magnets, and talk about how that phenomenon arises a little bit. Okay? So first of all, we've got the situation that you see on the top right. We have a wire. We are pretending this time that the wire, as it actually is, has some finite thickness. So instead of just saying like, ooh, there's a wire and we're outside of it, we're going to look at the thickness of the wire and assume that the current flows through a certain cross-sectional area. So if I were to start this problem by trying to find the magnetic field outside the wire, well, I would use an Amperian path that is outside the wire, and I would get the exact same equation that we got on 2 slides ago. So just for a current-carrying wire, we get the equation mu naught I over 2 pi r. That would be no different because I enclosed is just I. It's all of the current that passes through the wire. What we want to focus on here is the magnetic field at some distance from the center of the wire, but still inside the physical material of the wire itself. So for inside the wire, we're going to use that Amperian path where little r is less than big R, which is the radius of the entire wire. And of course, in this case, the Amperian path doesn't include all of the current. Some of it is enclosed. Some fraction of the total current is enclosed, and we're going to have to account for that. So let's see. B dot dl equals mu naught times I enclosed. As you might guess, the left-hand side is going to do the exact same thing as before. B is constant at that distance, little r, because it's the exact same distance from the center of wire the whole time. The integral dl is just going to be the circumference of the path itself. So the left-hand side of this gives me b times 2 pi little r. On the other side, we're actually not going to have to work too hard because I could think of I enclosed as just being a fraction of the current, which could be expressed as a fraction of the cross-sectional area that's there. The cross-sectional area is pi r squared, depending on whether we're talking about the little r or the big R. So we could say that let's just multiply the total current times some fraction of the cross-sectional area, pi r squared over pi big R squared. And that should give me the fraction of the current that's passing through the wire. Another way of thinking about this, if that bothers you, is like, well, why would I just come up with that all of a sudden? We've dealt with densities, charge densities, back when we were doing Gauss's law. You could think of this as a certain density of current that's through this cross-sectional area. I could say that this thing represents a current density, and then I'm going to multiply it by the particular area that I'm worried about. So really, we're doing the same sort of thing we did before. We're just doing it in 2 dimensions instead of 3. And then once we have that, we'll cancel some stuff out, solve for b, and then the problem's done, which I don't think that's terribly hard. Let's see, that's mu naught I times little r over 2 pi big R squared. Okay? Does anybody have any questions about the Ampere's law part of that? Sure seems easier than Gauss's law, right? Your question.
Will we ever have to do, like what we did with Gauss's law, of sometimes Q flow is just going to be the integral itself?
Yeah, so if there wasn't a constant current density throughout here, it could be. Yeah, I don't have an example like that prepared, but it's possible.
Current is like building up somewhere and not other places? Or like
It would have to be a case where maybe there's like a transverse magnetic field that's causing some of the charge to more build up on one side than the other. I can't think of another case, but there could be something. Notice the graph. There is a peak there in the magnetic field where the radius that I'm looking at is equal to the radius of the entire thing. In other words, I'm right at the surface of the wire where I'm including all of the current. So all of it is contributing to the magnetic field. And you'll notice as I go further inside, so as we go this direction on the graph, I'm including less and less of the current, so it makes sense that there's less and less magnetic field. And you'll notice that it is just linear. It's proportional to R, how far I am from the distance, from the center of the wire. Once we get on the outside, we're using the other equation, which is proportional to 1 over R. So as I get farther away, it's falling off as one would expect. Okay? Questions, thoughts? We've done 2 examples. One was like really quick, and this one was pretty quick too. They're not that hard, right? It worries you some, perhaps? Okay, we're not going to leave this yet. I'm going to show you a couple more cases of using Ampere's law before we're done, starting with the solenoid. The solenoid, we need to talk about a little bit because it's a common thing that's used to generate a magnetic field. Specifically, we can generate its own sort of magnetic field, but I can put it together with a magnetic material and generate an even larger magnetic field in the form of an electromagnet. Okay, we will see in chapter 30 that this particular apparatus can be used as another component in a circuit like resistors, capacitors, known as inductors. So we're going to examine that as well. So if you think about it, a solenoid really isn't anything terribly complicated, just like a capacitor wasn't anything complicated. It was just two conductors sitting really close together, and then all of a sudden all these interesting effects happen, and I can store charge, and it's quite useful. A solenoid is just a wire that we decided to wrap into little circles, which all of a sudden sounds like, well, that's not terribly impressive. Why would it do anything fantastic? Okay? So in and of itself, there's nothing special about the solenoid. It's just wire, and we've just decided to wrap it in this configuration. So you will notice that the magnetic field you get is drawn there on the top left, and it works out that you end up with a very strong magnetic field inside the solenoid going in one direction relative to what's outside. So comparatively speaking, between inside and outside, there's a tremendous difference. In fact, you can almost ignore the magnetic field outside due to the much, much stronger magnetic field in the middle. Okay? 1 second. As this gets longer, the more and more loops I have, that differential becomes even greater, and the magnetic field inside becomes even stronger in comparison to what's outside, okay? So you can imagine maybe the difference isn't that great with one loop. In fact, we looked at the magnetic field for one loop of wire, and it was like, oh, there's magnetic field inside, and there's magnetic field outside the wire. No big deal. But as I start to pile up loops, I start to get an additive effect down the center and a cancellation effect on the outside, and I'm going to show you how that works over on the right. Your question?
I was just going to say, this is kind of like that picture that we saw when we first started this, where like that hand, floating hand holding that wire, right?
Yeah.
Is that same concept?
It's the same concept for using the right-hand rule. So we can get the direction of the magnetic field through the center by either doing it that way and grabbing the wire, or I like to wrap my fingers in the direction of the current, and your thumb will tell you the direction of the magnetic field down the middle. I have to zoom in here just a little bit to see which way that current is wrapping around. You can see it goes behind the field first, so it's actually going this way. So fingers in this direction to indicate the direction the current's going around. My thumb points in the direction of the magnetic field right down the middle. Okay? Let's make a quick note of that. What do you say? So we'll say same right-hand rule as for one loop of wire. More questions about this before we dig into it a little deeper? Anybody? Anything? Nobody? Nothing? You got to finish that Lemonator. I'm coming for it. I'm telling you. Yes.
Again, like solenoid, like how the magnetic field works. Like, I'm not understanding this diagram, I guess.
Which diagram? The one on the left, or okay?
Yeah, it just, could you explain it more?
I think by explaining the right diagram, you might understand the left one more. Let's try that, and then ask me again if that doesn't help. Sound good? Okay. So let's see. On the right, imagine if we took the solenoid, as you see there, and just took a big knife and just went right down the middle of it, okay? This is a cross-section of the solenoid that you see on the left. It's right down the middle. So in other words, all of the top wires, considering the current is going up like this and around, right at the top, current is coming towards you in all cases. You can see that represented over here on the right by the little dots, but let's go ahead and maybe zoom in here and put a few little dots to indicate right at the top the current is coming towards you. And then it wraps around and goes into the screen, so right at the bottom of all of those wires, it's going away from you. We're only looking at right at the top and right at the bottom because I've sliced it right in half. Okay? Everyone good with the diagram on the right? Good so far? Okay. So let's do this. Let's start with the right-hand rule where we point our thumb in the direction of the current just for that first wire that's coming toward us. So if I do that, current's going this way. There's a magnetic field that wraps around that wire in the counterclockwise direction. So let's just kind of do something like this. Keep in mind that is happening for all of those wires at the top. Okay, so the one, a few over here, we're also getting something that kind of looks like that and wraps around. For all of these, we're getting that exact same effect. All right? At the bottom, thumb is going into the screen, so I get a magnetic field that's going around clockwise. So here, now I have a magnetic field that's going around this direction. And that's happening for all of them at the bottom. Still good? All right? So between the top and the bottom of the wire, you start to see that I'm getting this additive effect to the right. All of these are pointing this way. All of these are pointing this way. Everything is going to the right, and it's starting to accumulate and build on itself. On the outside, notice at the top here, I have, let's pick a good color. All of these are sort of adding up this direction. But don't forget, that's not all that's up there. The bottom wires, everywhere above them, have a component of the magnetic field that's pointing to the right. It's just farther away, but weaker. So you can imagine that all of these, they're creating the same magnetic field everywhere. It's just weakening by 1 over r as I get farther away. So you can see that we start to get at least a partial cancellation effect happening outside the top of the solenoid because I have components that are pointing in opposite directions. Okay? It's not a perfect cancellation, but it's canceling some. So when you think about them starting to build in between the set of wires and canceling on the outside, we're starting to get this separation in magnetic fields. It's stronger in the middle than it is on the outside. And you might imagine that down below, the same thing's happening. The bottom set of wires is giving me a magnetic field to the left, but the top set of wires is giving me something to the right on the outside that's serving to cancel. So let's say that outside at the top, let's do this. So down here and up here, partial cancellation of B. And in the middle, additive magnetic field. Okay? How's your question now? Is it better? Okay? That's the effect of all these loops of wire. The more loops we have, the bigger the effects get. Let me point out as well that this magnetic field that you see on the left is a whole lot like what you see for a bar magnet. You could almost think of this as like an artificial bar magnet. Instead of a piece of material, we're using current loops stacking on top of each other to create a magnetic field that has a high density and points out of one side and a high density and points into the other side. The solenoid has a north and south magnetic pole, just like a bar magnet would. Let's see what else I should add to this before we get to an equation. I think that's all of the concepts. Anybody? Anything? Questions? Are you alive? Yes. They're not all pointing to the left because I have to consider coming from the other set of wires as well. So all of the magnetic fields from this top set are pointing to the left up here, but this creates a magnetic field everywhere around them, including up here. And it's pointing to the right up in that region, which serves to cancel out the ones that are pointing to the left somewhat. So in all regions, whether I'm talking about the top, the middle, or the bottom, you have to consider the magnetic field from this row of wires and that row of wires. So the magnetic field coming from these up here is partially canceling the magnetic fields coming from these up here. Okay? In the back. What is the what? The purple rectangle. Thank you. You're leading us forward. I'm going to show you what the purple rectangle is. That was your goal, right? Let's just, boom, let's see what's next. We're going to use Ampere's law. Turns out that purple rectangle is the Amperian path we're going to use to calculate the magnetic field down the center, okay? So this will show you kind of, the flexibility of Ampere's law. We're not using a circle. We're using a box. And also, you would look at the situation and maybe be like, symmetry? I don't really know how I would approach this with Ampere's law. Allow me to show you. So let's start with integral of B dot dl equals mu naught times I enclosed. And again, our enclosure here is given by this purple path. Notice they have numbered the 4 sides of the purple path, if you can still see that under all of my scribbles. Hopefully you have something written down that makes sense to you, or watch this back later and scribble in something that makes sense and don't just take what I have there, because it's terrible, and I'm sorry. All right? So let's see. What is enclosed along those paths? You will notice that we have included, let's see, a few different wires here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 wires, all of which are carrying the entire current. Okay? So we're going to use that just like before. You have to consider all of the current that's passing somewhere inside your Amperian path. So we're going to do that. Instead of saying 12, maybe we could have picked any number, right? That Amperian path is completely arbitrary. So let's just say we enclosed N number of currents. So let's write it that way. We will say that the right-hand side of this is mu naught N times the total current I, where N is the number of loops that I've enclosed. Hopefully, we're going to do something to sort of at least partially get rid of that, because otherwise the magnetic field is going to be based on something imaginary, and that's no good, just like we didn't want Gauss's law to be based on imaginary things. And then I want you to consider all 4 parts of the path, 1, 2, 3, and 4, starting with 1. If I look at path 1, you will notice everywhere along path 1, the magnetic field is pointing in the exact same direction. Which means when I do the dot product, B dot DL, we're not going to have to worry about the sign. Sine of 0 is going to give us 1. And it's just going to be the magnetic field, whatever it happens to be, times the length of path 1. Okay? So let's write that down first of all. So let's see. B times L is what I'm going to get for this side for part number 1. What happens with part number 2? It's 0. Why is it 0? Yeah. So at least for the primary components of the magnetic field, in the middle and above, you're going to have the path be perpendicular to the magnetic field. And if you're worried about the fact that, wait a minute, in some cases, isn't there like a component up or down? Well, there's going to be enough of those up and down to cancel each other out. So we're not going to have to worry about any of those components. So B dot DL for path 2 is just 0. We're not going to have to worry about that. For number 4, over on the other side, also 0. What about for number 3? It could be negative BL, except we're going to assume that outside the magnetic field is negligible. Okay, it's much, much weaker than what's on the inside. For path 3, we also get 0. All of a sudden, this thing just became almost nothing. All right, so we could say that for 2 and 3 and 4, give 0. If some of those parts gave me another term, we would just have to add them all up. That's essentially what we did, was the part of the path number 1, 2, 3, and 4, adding 4 different terms together. Yes, sir. Make H arbitrarily big. Yeah, okay, so that line segment 3 is far away. Yeah, that works as well. Okay, so either assume that we have a solenoid that's large enough such that the magnetic field on the top is weak by comparison, or assume that path 3 is far away such that it's really not getting any magnetic field at all. In both cases, we get 0 for that part of the path. Okay? Somebody dropped something. Thought it was me for a second, but alas, no. That lemonade is still there. I'm just going to stare at it for another moment. It's bringing me joy. I'm just enjoying the cool thoughts that come with lemonade. I wish we had like a vat of iced coffee right now. Anybody with me on that one? Like just at the front, just like massive tub of iced coffee. One that you could like swim around in. Not that you do that. And then drink it. None of that's happening. No, just ignore all of this. Let's rearrange this for B. So I've got B is equal to mu naught I n over L. N over L. Remember that the number of loops we decide on is arbitrary, but also the length of our Amperian path is totally arbitrary. But N divided by L actually has meaning. That's essentially a loop density. How many loops per length do we have? So I can rewrite this thing as a loop density, which is a measurement of, well, how many loops we're packing into a certain space. It's how tightly wound this particular solenoid is. And we're going to give that a symbol of its own, which is just little n. So we'll rewrite this as mu naught little n times I, where little n is the loop density. And then we've got the equation for the magnetic field down the middle of the solenoid. Okay? How much fun was that? Uh-huh. Who wants to go outside now? Yeah, I thought so. More of you are like, I can't take this anymore. Yes? From the other side of... From the wires at the bottom. Huh. That is a good question. Keep in mind, for Ampere's law, only using what's enclosed is enough to incorporate what's on the outside as well. Because of one of these, it's because the B dot dl integral is actually taking into account everything that's happening on the outside, and it's giving like a cancellation effect on one side and an additive effect on the other, such that the sum is still the same. It's essentially what was happening there in that diagram, just sort of writ large with a bunch of loops of wire. Otherwise, it's the same concept. Anybody else? Ampere's law once again on the next slide. What if we take the solenoid and wrap it into a circle? Because that seems like a logical thing to do, okay? And we have something that we would call a toroid, and you will notice here we just have the same thing. It's just wrapped around some other piece of material, and we will see that that could also give rise to some interesting magnetic fields. But I'm going to show you how we can use Ampere's law to calculate the magnetic field down the center of the toroid in this case. So here's one thing that we can say, first of all, is let's zoom in on this and see which way the current's going. So the current's going around like that, which should tell you something about the direction of the magnetic field through the coil of wire. Well, if it's going around this way, looks like the magnetic field is going to be going through the center sort of that direction. So in other words, everywhere around the circle, we could say that the magnetic field is going clockwise around the toroid. Magnetic field is going clockwise around the toroid. So again, it's passing through the center of the solenoid, it's just now that that solenoid is wrapped in a circle. You can see this illustrated down below, where they're showing, again, a cross-sectional cut of just a little piece of the toroid, and we have, well, parts of the current on the outside are coming at you, and the parts of the current on the inner side of the toroid are going away from you, and you can see that the magnetic field is going all the way around in the circle in the direction that's shown there, in a clockwise direction, okay? So, let's see. We are going to use this path number 1. Path number 1, which you can see is drawn where we're finding the magnetic field through the center of the circular solenoid, if you want to think about it that way. And we're going to use that with Ampere's law to do a calculation. So B dot dl is mu naught times I enclosed. And again, for I enclosed, well, I have enclosed a lot of loops of wire that all have current passing through them. So I'm just going to express that once again as N times the current that's in any one of those wires. What happens to the left side? Anything different? Surely doesn't look like it. B everywhere there is going to be constant. The integral dl is just the circumference of that particular path. So that's going to be B times 2 pi r. And then we're essentially done. So B is going to be mu naught n times I over 2 pi r. And again, that is inside the toroid loops. Two quick notes. What about path 2? How much current is enclosed by path 2? Yeah. Yeah, we're going to have to be a little careful about that part. So kind of allowing this part to be negligible. What is the total amount of current that passes through path 2? All of it? 0. Ooh, those are very opposing answers. I would agree that it is all of it. And all of it adds to 0. So you're both right, which is kind of fantastic, okay? It is all of it, but it is all of it out of the page and all of it into the page. So those are two different directions. They're going to cancel each other out. So we could say that I enclosed is 0, which means that everywhere along path 2, the magnetic field is essentially 0. What if we picked a path 3? I don't think there's too much to think about here. Path 3? Well, also 0. Okay? And then I think we're pretty much done with that particular problem and done with Ampere's law for now. You feel good about Ampere's law? That's just, you're just like, yes, I do. What's your question?
So the whole loop density concept, does that not come into the toroid at all?
We could, trying to think if there's a way we could express a loop density there. We could rearrange things that way, but for whatever reason, I left the answer in this form. Yeah. Yes. Are they related at all? They are. We'll see how in chapter 31. At this point, we are considering them to basically be separate. Mu naught is always related to magnetic stuff. Epsilon naught is always related to electric field stuff. Once we start tying those two concepts together, those two things become intertwined. Yes? N over the diameter? Yeah, so we could, or rather over the circumference is down there. Yeah, so, yeah, you could express that as a loop density if you wanted to. Yeah. As a thick wire? There's current flowing in the wire part, but not in the green section. The green thing that we see there is some sort of insulator. So nothing is actually flowing clockwise, per se. They end up making a motion clockwise. I would agree with you there, but it's a complicated way to go clockwise. Does that... I would say that this is accounting for that clockwise motion and giving you the magnetic field anyway. Because all of them they're doing this, and I would agree that as they do that, they're sort of working their way around clockwise. But if anything, either this is including that effect or that clockwise motion is small by comparison to the other effects that are happening. Assuming I'm understanding what you're saying correctly. Yeah, okay. Over here, yeah.
What if you were to have a
toroid inside a toroid. So like a smaller one inside the other one. I'll let you do that problem. It's a good question. Sounds to me like two interrelated donuts, and it sounds tasty. But the same concepts, I would just treat them as a superposition more than likely. Do the two problems individually. Anyone else? Yes. Intuitive, it's again one of those things where you have the cancellation effects on the outside. In this particular case, we're getting 0 just in the same way we essentially got 0 here. Is it 0, 0 or just approaching 0? That's kind of hard to say. Yeah.
And you just said that the whole current canceling for that would be 0 was just because they're coming in and out like that, like the dot and the X?
Yeah, it's because in every region of space there, I have to consider the magnetic field from both the wires, both top and bottom parts. All right, let's slide over to our last big thing in this chapter, our last big rule for calculating magnetic fields from currents. And you could think of this as basically how to calculate B from any current configuration. The only limitation will be your math skills. This equation can handle everything, but of course, as the situations get more and more complicated, the math gets more and more complicated. And we'll take that part of the way, but we're not going to go into ridiculous situations. So here's the thing. Let me just start by writing the bios of our law, and I'll show you how we're going to use it. We can say that a little bit of the magnetic field is equal to this thing, mu naught I over 4 pi times dl cross r hat over r squared. And I think this one just turns into everybody's favorite, and of course I'm lying, because it does get complicated. So what we're saying is that we have a wire that is in some configuration, and it's carrying a current, and near that wire at some point, I want to find the total magnetic field at that point from all the little pieces of wire. So you can see in this particular diagram, we have this wire that's, well, it starts out straight, but then it decides to be kind of curvy and a little bit wavy, which means I can't just use the equation for a long straight wire. It's not that simple. If it's straight, well, then the bios of our law is going to reduce to what we got with Ampere's law and that first equation we used for currents. So in this particular case, we are going to say that every little piece of the wire, dl, is carrying the same current I, and we are only concerned about finding the magnetic field at this one point P as a result of the current everywhere in the wire, okay? So first of all, we've already used dl vector several times. It is just a vector that is a piece of the wire, and it points in the same direction as the current. The r hat vector is a unit vector, and we will say that it is a unit vector that points from the little segment dl to point P, where we're trying to find the total magnetic field. Don't forget that unit vectors all have a magnitude of 1, which is going to simplify that cross product a good bit. So if we have a bit of current that's passing in this little piece of wire, notice from that point out to point P, our r hat unit vector points. So it's basically just saying, here I am at the current, I want to find the magnetic field over there. It's just a pointer vector to give you some information about an angle between the direction of the current and over where you want to find the magnetic field. Okay? We are going to do an example with this on the next slide just in case you get confused. So the process of this is essentially always going to be the same. If I want to find the total magnetic field, we're going to have to integrate dB, which is going to mean evaluating this cross product to begin with. And then there's going to be a lot of constants that are in there that are typically going to come out. And many times you're going to end up with an integral that's in 1, 2, or 3 different variables, and you might have to do some substitutions to try to get it down to 1. And depending on what the shape is, that could be difficult, okay? Let me show you how this works on the next slide, and I think all of it will make just a little bit more sense. Using a current loop. So for starters, this diagram tends to confuse people because at first glance, it just looks like there's a small bar that maybe has a current in it. This is a circle, a circular loop, and we're looking at it edge on, okay? So keep in mind that, first of all, it's a current loop. At the top, the current is coming out towards you, and then it wraps around and goes into the screen at the bottom. Are we all clear on that to begin with, okay? We are trying to find the magnetic field at a point P that is a distance x from the center of the current loop, okay? Clearly, we could try to do this calculation at any number of points, but calculating it somewhere in the middle is going to allow for some symmetry that will make this calculation easier. And also, I think that if you think about this too much, it's a little bit depressing. All the work that we do in any of these problems is just to calculate the total magnetic field in one location. What if you want to find the magnetic field at all locations around this particular current loop? Clearly the calculations are going to get quite severe as soon as I want to find it at 2, 3, 4, 5 points. If I want to find it anywhere, everywhere, well, we might be here for the rest of our lives, and I don't think we want to do that. We would incorporate some computers at some point, okay? So we're only trying to find the magnetic field at this one point. You will notice that the vectors that they've drawn there are representative of the magnetic field that's being created only due to a little segment of the wire that has current at the top. So it's only considering that exact point where the current is coming towards you. Still good? Let's use that little bit of current to make sure that those vectors make sense. So at the top, the current is coming out of the screen, which means that the magnetic field around that little segment of wire at the top is going counterclockwise. So in other words, maybe we draw like a full circle here. Something like that, which tells me the direction of the magnetic field that's coming just from that little segment of wire all the way around. And once you do that, you can see that this dB that they've drawn, well, that is tangent to r, the distance I am from that little top. So it makes sense that that would be the magnetic field that's coming from that little segment. Let me pause for a second and make sure that you're on board with that. Yeah. That is the magnetic field at all the other points due to that little segment of wire at the top. Just, I can't draw all of it. It would make a complete circle that goes around. Some of it does, but not all of it. Let me show you by looking at a point at the bottom. So with a point at the bottom, the current is going into the screen. So we have clockwise magnetic field. So maybe we do something that sort of looks like this. There would be a distance over like that, which we would call R. There would be a magnetic field that's perpendicular to that. And then it would go around this way. Okay? So if I look at those two vectors, again, this is going to represent a little bit of dB just coming from the bottom little piece of wire. You can see that we're going to have up and down, or perpendicular components that cancel out, and we'll have components horizontal that add in both cases. Okay? We've only considered the top little piece of wire and the bottom little piece of wire. We need to consider the entire loop of wire. But I think using that little bit, you can sort of see how the dB vector and its components will rotate around in a circle. So no matter where we go, we're always going to have a perpendicular component that's canceled out by another one, and all of the parallel components are going to add up. And by parallel, we mean parallel to the x-axis. So let's write down a couple of notes here. Somewhere I actually have this problem worked out. There it is. So we'll say that the perpendicular components cancel. and the parallel components add in the positive x direction. Questions? Questions before we actually do this? Anybody? Anything? No? Still no? If I wait long enough, a question always happens. So now we're in a waiting game with each other. Yeah. If I stare at you long enough, eventually you'll ask a question. It's just how it works. What was that? I don't know. Where's a question? That was a question. Ooh, that was a question. That was sneaky. Huh. Do you have a question, or are you just commenting that was a question? Okay, yeah. Do you want to, ask a question that leads us to the next thing like you did earlier in the lecture? I got you this time. Ooh. What was that? It's quiet. I like how you sounded sincere, too. That was good. How would we calculate B? Yes. To what end? To see the cancellation or the entire thing? I don't know. I'll let you play with it. Let's write out the bios of our law for this case, and specifically we're going to be looking at parallel components. So dB is equal to mu naught I over what? 4 pi. There's an r squared in the denominator, and then we have dl cross r hat. If we want to find the total magnetic field in this case, it is simply going to be the parallel components. So let's write that as B parallel, not 11, parallel. And that's going to be equal to the integral of dB cosine phi, where phi is given there in the diagram. And then let's take that dB from above and plug it in below. So now we've got the integral of, let's put the cosine phi out front, of mu naught I over 4 pi dl cross r hat over r squared. Well, that looks like fun. And once you've written that down, we're going to change the cross product into its magnitude. And then very quickly, this one at least is going to simplify for us. So this is equal to cosine phi mu naught I over 4 pi times dl. What is the magnitude of r hat? That's just 1. I'll put the 1 there just to keep things straight. Times the sine of theta, where theta is the angle between dl and r hat. And I forgot the r squared in the denominator. So what is theta in this particular problem? Where's r hat? R hat points from dl over to the point P. So r hat, let me switch colors again, would point in this direction. And it always just points from whatever little segment you're looking at over to point P. So what is the angle between dl and r hat? Sure? What's that? They are perpendicular, and they'll always be perpendicular. dl is perpendicular to the screen, and r hat lies in the plane of the screen. Those have to be perpendicular to each other at all times. So that means this thing is going to be 1, because theta is equal to 90 at all points. Which helps a little bit, Let's see, what else can we do here? So I'm going to try to get everything in terms of R, and it turns out that the R is a constant we're going to be able to pull out. So we could rewrite, you got to love this color combination. We could rewrite cosine of phi as, let's see, big R over little r. Then we still have mu naught I over 4 pi dl over r squared. No matter where I go in the loop, the distance from the dl over to point P is just going to be a distance r. So that is constant every single time. So let's start to pull that out. So now I've got mu naught I r over 4 pi r cubed times the integral dl. Let me pause for a second. Everyone caught up? It makes sense. Do you have a question so far? You gotta love it when nothing's left but the integral of dl. That's always everyone's favorites. So the integral dl is just going to be what? It's the circumference of the current loop itself. So now we have mu naught I r over 4 pi little r cubed. And that integral is going to give me 2 times pi times big R. So we could rewrite that as mu naught I, we can get rid of some things here. Let's get rid of that and a 2 there. So mu naught I R squared over 2 R cubed. And tell me if I made a mistake there somewhere. I think it's right, but I could have done some algebra wrong. Questions? Biot Savart. You get the basic idea. Most of these are going to start the exact same way, just getting the integral set up and sort of getting to, like this point. It's there that all the complexity lies and everything changes after that depending on how difficult the integral might be. So, should we try a different point? Maybe as practice. I'm not going to do this now, but you could do this exact same problem, but just pick some other point to find the total magnetic field and see what issues you run into. Like, I don't know, pick a point directly below that distance x, maybe directly in line with the bottom of the loop. There's another problem. Give that a try and see if you can do it. Question over here? No? I thought I saw your hand a second ago. Did I not? Yeah. Okay. Okay. Question? We are taking into account all parts of the loop by doing the integral. So we started sort of taking it into account by looking at the vectors and see what would cancel out. And then by actually integrating all the way around the loop, we're adding up all of the parallel components. And the perpendicular ones canceled. Who's ready to go outside? Or maybe you people are like the inside people. Is there a chance of that? No, you're not inside people? I'm inside people. Yeah. Outside's nice, but, inside's nice too. Maybe inside's better. Inside has like air conditioning and something to drink and lemonade and, lights and all of you. Okay, maybe not. Okay. All right, last thing in this chapter. We've got 1, 2, 3 slides left here, and that is sort of a rough look at magnetic materials. A very rough look at magnetic materials. To actually explore this topic fully would require quantum mechanics, and I don't think that we really want to go there since we haven't talked about that at all yet. Take another class and then revisit this. I just want to give you the basics at this point. So we're going to look at 3 different magnetic phenomena that happen in materials, starting with ferromagnetism. Ferromagnetism. You could say that ferromagnetic materials there's just a few of them. The most common would be iron and a few other materials that can be made into strong magnets. That is vague, I know. because they're the only ones that have the necessary quantum structure to give that to us. Okay? So here's the basic idea. In a material such as iron, they are composed of little magnetic domains. These are little regions that have sort of their own little magnetic field. You can think of them as like little tiny bar magnets if you want to. These magnetic domains, if you're wondering, are less than a millimeter in size typically. And for the most part, assuming we haven't taken the iron and done the process to make it into a strong magnet, well, these are all just going to be sort of randomized throughout the material, and the material itself is nothing special. All of these little magnetic domains have magnetic fields that are pointing a bunch of different directions, so the randomization should overall cancel out the total magnetic field. The thing is that if you apply an external magnetic field, we will say that components in alignment with it start to grow. So if you take a look at the comparison between these two diagrams, notice they are creating a magnetic field from the outside that's to the right. And just take a look at any of the little domains in the top diagram that point to the right, and you'll see that they're now larger. This is actually somewhat of an accurate diagram. So notice this one, that little domain was this sized. Ooh, now it's grown this large, okay? So the ones that are already in alignment with the external magnetic field start to sort of take over the material, and ones that are not in alignment are now taking up less of the overall material, which means that you're going to get sort of an induced magnetic field in the material itself that's in alignment with this external magnetic field. At this point, I can take away the external magnetic field, and the material itself now has its own magnetic field that is somewhat permanent at this point. We have physically changed the structure of the material, and it's sort of stuck that way at this point unless I do something to unstick it, I guess, for a better term. And there are a couple of different ways that we can do something like that. One thing you can do is, like, this is a physical change in the material. You can just throw it on the ground. Like, weirdly enough, this is just physical alignment of things. You could just take the iron and hit it on the table, and you'll tend to more randomize the structure once again, and magnetic field gone. That's kind of depressing and sad, but also kind of cool, because I'm taking something that's happening on a really, really small level, and I can just change it that easily, okay? So ferromagnetism is any material of which there are only a few that tend to have this particular ability. Let me add to this that we could say there is a new magnetic permeability that is not mu naught, but the magnetic permeability of the material. In a sense, it's kind of like permittivity was. It tells us something about how well magnetic fields can propagate through that particular material. So, let's see here. Let's slide to the next slide, and we're going to see this little structure once again. That green that's inside the toroid is supposed to be iron. Yeah, iron is green, always. Who knows, okay? So what we're doing is we're taking a ferromagnetic material and putting it in the toroid or in a solenoid, and we're letting the solenoid or toroid create the external magnetic field that serves to cause alignment in the ferromagnetic material. And then all of a sudden I have a magnetic field coming from two places, from the current in the wire and also from the alignment of the magnetic domains in the ferromagnet. So both of these are happening simultaneously. So we could say that B total here is going to be equal to B naught. We'll say that that is what is coming from the wire, or from the current, plus B, and for whatever reason, they use M in the textbook, which is from the material. So you have a total magnetic field that's coming from both. typically Bm is going to be much, much greater than B naught. You're getting a much larger effect from the material itself. In addition to this, we could say that the magnetic permeability of the material is going to be much, much greater than mu naught, which is causing this to happen. So let me see if I can describe these two graphs and give you some feel for how the material responds when I increase the magnetic field and it starts to have an alignment and it gives me an additional magnetic field. And then what happens when I turn off the external magnetic field and I'm left with a magnetized material. So first of all, notice the graph in the middle. This is just a graph going from a zero state when the material is not magnetized at all, and also there is no current in the wire at all, which indicates that B naught is going to be zero as well. So this is at the beginning. The current is equal to zero, which means that B naught is equal to zero, and B sub m is equal to zero because I haven't done any magnetization at this point. Now you might expect B naught, as I increase the current, its magnetic field should increase linearly. Based on the equations we've had here previously, at least the one for a solenoid and for this one, like as I increase the current, notice it's right there in the numerator, I should get a linear response to B. However, as I look at this graph, this is the total magnetic field. The total magnetic field, the sum of B naught, which is a linear response, and that coming from the material itself is nonlinear, okay? Instead, you get a curve that looks something like this as I ramp up the current. Yes, sir? Where is the North and South Pole? I don't know that you could clearly define one in that case. Yeah. I think that would be difficult to define without seeing the full picture of the magnetic field. I don't know that there is one. Yeah. Anyone else? Yeah. Would it start to move? No, it shouldn't move. It's going to be fixed in place. It has nowhere to go. You want it to just rotate inside there? There are no forces in that direction either. Yeah. Okay? So from A to B, do you see what's happening? Are we good so far? Yeah. The iron and the wires are going to be insulated in some way, such there is no contact there. Yeah. We're just not showing that for simplicity. So from A to B, we are essentially magnetizing the material. At this point, you could say that this is about 70% saturated. In other words, to its full possibility of magnetization. The thing is that it might as well be as far as you want to go, because typically, let me make sure that I get this number right, I would have to ramp up the current another 1,000 times to go from 70% to like 99%. Basically what happens is early on, the magnetic domains are relatively easy to align, but as I align more of them, trying to get the smaller ones to like fall in line and come into place, it gets more and more difficult the farther you go, which means that this would continue to rise very, very, very slowly and eventually get there, but who in the world wants to go to that effort to get that result, okay? So that's about as far as we might want to go. So in this point, if we were to take this curve and go to the next graph, you'll notice this A to B curve is now positioned on a larger graph. That's exactly the same as before. And then we're going to go from B over to C. In this process, we're going back to the left, which means we're ramping down the current. So the material has responded, and now we're turning the current down. You will notice that what doesn't happen is it doesn't go right back down along this curve because the material itself is staying in that condition, all right? So as we go from here to here, at this point, again, there is no current. This is the magnetic field that remains from the material itself, all right? So we could say at that point, C, I is equal to 0, and B naught is equal to 0. That is only the magnetic field that's coming from the material. It has some permanent magnetization. But then we could keep going, and we could go over to point D. At this point, we're going negative with the current. So we could say here we have reversed the current. And now we would begin creating a magnetic field that's external but in the opposite direction. So you might imagine at this point like we're doing work to try to flip the magnetization domains the opposite direction, which at some point we can actually do, and that would be once we get to this point where there's no total magnetic field, or there's no magnetic field in total, and then we can continue to ramp current that direction and eventually get it to fully magnetize in the opposite direction, get all the magnetic domains to go the other way. So let's add a point here. We'll say that this is magnetized in the opposite direction. And then eventually we could get back to point B by, again, ramping the current in the original direction once again, and we could get back to this point. But you will notice that we never sort of cross the path that we did before. This is what's known as a hysteresis loop, and it's simply because of friction. We're mechanically trying to flip the direction of these domains, and, well, that takes some energy, which means that it just doesn't go back along the same path as before, and there's an energy loss in this process. Essentially, what's going to happen with a graph like this distance between point C and point F, the wider this hysteresis loop is, the better that material can be magnetized. Because remember, at point C and at point F, that's when I don't have any current. That's simply the magnetic field that's coming from the material itself. So the wider apart those 2 points are, the better, assuming you want a larger magnetic field. Okay? I don't think there's anything that I want to add to that description. So we've got one slide left. Yes?
So like you said, when the only like kind of way to go from, we've gone around that whole loop, but if you want to really go back to original state, there's only a couple ways you can do it.
There's a couple different ways you could do that. First of all, throw it on the ground. That's a rough way to do it. Another way would be to try to go around the loop, but every time you work your way around the loop, you don't go back to that maximum current. So it's kind of like you do something that sort of looks like this. You would, as you go around the loop the second time, maybe you would kind of go inside that a little bit, and you could slowly sort of work your way back to zero magnetization. But that takes some effort. Yeah. Could I go to point G and stop the current, and then we're back at point A? Let's see. So at that point, that seems like it would make some sense. I would agree with that. Yeah, it's a good question. I don't have a good answer for that. It seems like you would bounce from there over, but there must be some residual magnetization at that point. Anyone else before we do the last slide and wrap up the day? Yeah. Yeah, basically. Send in the current the opposite direction, change the direction of the applied magnetic field. Yep. Okay? That is ferromagnetism. These last two, I'm essentially just going to roughly describe and give you a couple of equations in case they come up. Both of these effects are much, much less significant than ferromagnetism. So there's a lot less that's going on. Here's what we can say about paramagnetism, and that is all materials are at least a little magnetic. All materials are a little magnetic, which means we can say in all cases, mu for the material is greater than mu naught a little bit. Essentially, we're dealing with charges in any molecule. All of them could be said to have some dipole moment. So while you don't have the larger magnetic domains, you can get a little bit of alignment with the molecules themselves, but not a little bit, not a lot. And that's going to give you a little more magnetic field coming from the material. this just isn't a strong effect, okay? So the material, it's like, it really doesn't want to be a magnet, but you can cause it to generate a tiny little magnetic field by giving it an applied external field. Yeah.
Why were we removing wires and such? Why were we using mu not when the wire is like copper or?
It's an approximation. It's close enough to mu naught for it not to matter for what we're trying to do. Good question. So let's see. This is coming from the dipole moment of molecules being aligned. A couple of terms here that you might want to know. First of all, something known as relative permeability. This is just something that compares the permeability of the material to the permeability of free space. And for that, we're going to use a kappa sub m equals mu over mu naught, or excuse me, not mu naught over mu, but mu over mu naught. So it's just a ratio comparing how much larger the permeability of the material is to the permeability of free space. And then there's also something known as the magnetic susceptibility. And for that, somebody tell me what that Greek letter is that I tried to draw. Who? It's kind of like a curvy, wavy X that kind of looks like chromosomes. Who? Chi? Is it chi? Are you sure? Chi? Chi, chi, co. I don't know what's happening. So let's see. That is just equal to Km minus 1. So it's just telling you how much more susceptible to magnetic fields it is than free space. And then finally, diamagnetism is even weaker than paramagnetism. And this is a weird case where mu is less than mu naught. It's less susceptible than free space, so that means that kappa sub m is going to be less than 1, and whatever this Greek letter is going to be less than 0. So a couple of notes here. This is weaker than paramagnetism. And what happens is there is no dipole moment for the molecules, and instead you get an induced dipole moment. So we're sort of making something happen that's not there, but this is in the opposite direction to the external magnetic field. If I remember correctly, there was a lab that works with like the National Magnetic Field Lab, I think the one at Florida State. They use diamagnetism to levitate frogs, which, like levitation, that would make sense because you're getting an opposite internal magnetic field to the one that's internal, so there's going to be an opposing effect. And I don't know why you want to levitate a frog, but alas, you can go find pictures of that. No frogs were harmed. The frog looked happy. We are done, except I will encourage you to look up one additional video that maybe you have not seen. They took mice to space, and then they filmed them. And it was kind of hilarious.